No, but the problem is the stuff in the first midterm is what? Kirchhoff voltage law, Kirchhoff current law, nodal analysis. So I'm not going to quiz you on that as such, but I mean, you have to know how to do Kirchhoff voltage law, Kirchhoff. I mean, it's sort of built in. Yeah. Man, come again. So what's the problem? I don't understand. Okay, so you want the exam to be Monday? Okay. So exam is April 13th, as we agreed. Okay, so okay, and it's recorded, so everybody's okay with that. Okay, so let's see. So op amps is we'll work on chapter 14. So an op amp is a integrated circuit device. So it's an IC. So if you open up your phone or any other electronic device, you'll see these black semiconductor devices, which chemical engineers have a lot to do with, right? So chemical engineers, a lot of time they work in process control in such semiconductor plants, right? So it's a lot of chemical engineering actually, it's a lot more than electrical engineering. So electrical engineering would design the devices in their offices, etc. But the process itself is a lot of chemical engineering behind it. Yeah. So an op amp is just like any other integrated circuit. The basic, sort of the simplest integrated circuit is a simple transistor. We did not really study transistors, but you can think of transistors as nothing but a switch that has, a contact resistance. Right? If you want to think of it that way. So we will not really study transistors, but let's say we have a circuit that looks like this. You have a source here that you can control, like a controlled source, and with a transistor, this is an example of a simple transistor circuit. Let's say you have a resistor here and another resistor here, and you would like to control some output voltage across this resistor, and you want the control of the output voltage from this resistor to be controlled by this source that you're controlling. Like this is the source that you're controlling, and you would like to control an output voltage in a certain way. So you want to make this small, this V output, you want to make it small or big, something that's it's an application thing. Some applications require it small, some applications require it big, and your source here does not have the power to source or to supply a lot of current. It can provide a voltage signal and a small amount of current, right? A typical application is a sensor. A sensor is not a generator, right? A sensor is used to measure a physical phenomena and provide a voltage or a current signal that you would typically, chemical guys, maybe in your process control lab, you were exposed to 4 to 20 milliamp devices. Did you take a process control lab? No? So you may be measuring flow, and they will tell you that the output is 4 to 20 milliamps. This is very typical. A 4 to 20 milliamp output is very typical of a typical sensor that's used in a process as a process instrumentation sensing device, right? So it's able to give 4 to 20 milliamps, or 0 to 1.8 volts, or 0 to 5 volts, or 0 to 3 volts, etc., etc. But what if you want to create out of that something that is, once you have this flow signal happening, you want to run a motor. A motor requires a much higher voltage and a much higher current, right? Let's say this motor would then close a valve, for example, right? This motor will require a much higher voltage and much higher current. That is not going to be provided by your sensor. You want as soon as your sensor reads 3 volts, that your motor turns on and closes the valve, for example. So initially it was 0. As soon as it's 3, motor turn on. So you want the motor voltage to be, 100 volts, for example, when the sensor voltage is 3, or somewhere in the middle to control the flow rate, for example, using some vane, for example, right? So in that case, you will want your sensor signal to be sort of isolated from your motor power circuit. You want them to be related by in a controlled fashion, right? So when this becomes 3, please turn on the motor. When this becomes 1, turn on the motor halfway or turn the vane halfway, right? So what we've studied before from the filters that we studied before, we could have done this, for example, using a low-pass filter. Let's say our frequency of our sensor, let's say it's not a 1 volt or 3 volts continuous, let's say it permits, it's a certain, this sensor provides an AC signal output with a certain frequency. What this low-pass filter does is allow the low frequency to pass. So as soon as you see low frequency, then there will be output voltage across here, and I can turn on my motor. For example, let's say this is a motor, right? For example, right? This case is not something that is practical because here I have a sensor. I do not have a generator really. I have a sensor that provides some signal in a certain frequency range of interest. When it's low frequency, this circuit here, my low pass filter that we studied in the previous section, allows the signal to pass through as it is. But it takes its current. Remember, the current is coming in from this source here. You know, our output voltage here is nothing by, it's governed by Kirchhoff voltage law. The output is equal to the voltage across, the input multiply this impedance over the sum of the impedances, right? Kirchhoff voltage law, the voltage divider rule, right? This is not logical. It's not a logical way to run a motor. You know, here, if it's high frequency, you know, the capacitor will act like a short circuit, so it will attenuate the signal, so the motor will not see a voltage in that case, right? So it did sort of this logic that we want, right? But it depended on the fact that this sensor was able to provide enough current and voltage to run the motor, because it's a circuit here. This motor is nothing but, think of this motor as a load, a resistance. At the end of the day, this is a circuit that looks like this, right? That means this source has to supply current to this branch and this branch, which is not possible with a sensor. So what do you do? One step that we would not study or we skipped is, you know, using simple transistor circuits. So that's sort of the intermediate step between, you know, the passive analog circuits that we studied for low-pass filters and high-pass filters, and what we're going to study today as op-amps, right? So between them is what is the basic transistor circuit. A basic transistor circuit works, you know, let's say simply, I'll call this VG, for example. Sorry, can you see this source? It's a source, okay? The battery, for example, a high power source. This is a high power source. This is a high power battery, and what this and this resistance some value, this resistance, and this output is your motor in this case. This resistor here is indication of the motor current. Okay, so what do you want to do? You would like, as soon as your sensor value reaches a certain level, 3 volts, for example, that this motor or this current through this resistor to such that a certain, you know, which corresponds to a certain V output. Right? I would like that to happen. So what transistors do is they act like a switch with a resistance in series, simply speaking. But a controlled switch with a resistance in series. Right? So what does this mean? It means that once my sensor here, my sensor tells my control, the brain of the transistor, okay, I want to start providing some value of current. And this will be a variable. This resistor here internally will be variable as well. So it's like a switch with a variable resistance in series. This is what the transistor looks like. It looks like a controlled switch with a variable resistance in series. This means that fine, I can give a signal for the switch to close. And hence, if I give a signal for the switch to close, the circuit would look like a certain value. So this circuit here would look like this variable resistor that's inside my transistor, with this top resistor here, and this bottom resistor that I'm measuring the output across, and a source, VG, right? Does this have anything to do with my sensor? The sensor just gave the control signal to close. Okay, you block here, you transistor, I want you to look like a variable resistor. and the value of current here, the 4 to 20 milliamp in your flow meter measurement, or the 1 to 5 volts, for example, in another sensor, this is going to determine the value of this variable resistance R. Right? So I sort of created an output voltage here that is controlled by my input signal, which is my sensor output. But the power to run this, or to supply this resistor here with current, is not coming from my sensor. It's coming from this generator here, this DC source, this battery here. Right? So it's canvas. Put it on white background. It's easier to see. Right? So I had a sensor here that just provided a signal to this transistor, and I had another resistor here, a source here, and this was my load V output. Right? This, as soon as I gave a certain value of current, let's say 4 to 20 milliamps, here I require, I don't know, 10 amps. For example, this 10 amps is not nowhere close to 4 to 20 milliamps. I require 10 amps for this resistor to produce the certain amount of heat this process requires. Right? So how do you go about it? You have to put some circuitry in the middle. And it cannot be a simple low-pass, analog low-pass filter or passive low-pass, high-pass or low-pass filter that we studied before. It cannot be analog electronics, because in that case I'm relying on the power from that sensor to supply my load. Because again, my load now looks like this resistor, my low-pass filter looks like this is my sensor. They're all connected in one circuit. I will have to do Kirchhoff current law, Kirchhoff voltage law, find out the currents. It's a simple AC circuit that we studied, right? That is not the right way to run a motor in a control process. You would use a transistor, for example. And what it did was sort of amplify the effect of my sensor's input, right? So it took this 4 to 20 milliamp and made it, I don't know, 8 to 10 amps. How did it do that? As soon as it provides 4 milliamps, this transistor turns on and becomes a certain value of variable resistance. And this is my VG, and this is my V output. So this is going to be defined by the transistor's datasheet. You do not select this. You select this based on the transistor datasheet. So you go and select a transistor that has a certain voltage current, like a capacitor. Capacitors have, if you put a certain current, a certain voltage will develop. The relationship between them, IC equals C dVc by dt, right? This is, if you pick the specific capacitance, then the voltage current relationships are defined for you by the capacitance that you selected, correct? Same thing with a transistor. If you select a specific transistor, you will have certain curves here that come along with the transistor. These curves are going to tell you the voltage across this variable resistance, this V, the voltage across this variable resistance V, and the corresponding current flowing through it. If you have voltage V and current I, can you define a value of resistance or not? V equals IR, right? What you did was, based on the value of sensor signal, this 4 to 20 milliamp, you will go and choose one of these curves. You will choose one of these curves. That's what the transistor does. As soon as it gets a signal, it looks at the signal. You are 4 milliamps. Okay, I will go to my characteristics. These are transistor characteristics. The transistor characteristic has, relationships between voltage and current. We know that the relationship between voltage and current is resistance, right? The relationship between voltage and current is resistance. So, I got a certain input signal, 4 milliamps. I will go to one of my curves. This is 1 milliamp, 2 milliamp, 3 milliamp, 4 milliamp, 5 milliamp, for example. I got a 4 milliamp signal. So I will go to the 4 milliamp curve. I go to the 4 milliamp curve, and I know that my load here requires, 5 amps. So I go to 5 amps here. This will correspond to a certain voltage across the terminals of the transistor, V. Right? So I have a V and an I defined, which means I have an R, sort of, for the transistor. So every time I change my gate signal, this is called my gate signal or control signal. Every time you change your control signal, you go to a different curve. You go to a different curve. You still need 5 amps at the output, for example. Your load requires 5, this motor requires 5 amps to move the vane or whatever. But it will correspond to a different value of voltage, which means a different value of variable resistance that you plug into the circuit. Right? So with this transistor, you can control, for example, a certain voltage at the output using the sensing, the information from your sensor. Right? And the power or the current that's flowing in this circuit is going to be drawn from this external source. This external source is the transistor's power supply. Anything requires a power supply, so the transistor's power supply, external power supply, is what's going to provide this current. It is no longer your sensor. But you see the difference between, the simple passive circuit, low pass filter, high pass filter, whatever analog circuit that we studied before, and a transistor circuit. Okay, so the main thing is you're deriving the power of the output from an external source, and you're able to manipulate the output. I can manipulate the output by providing variable control signal input. Right? That's what this transistor circuit does. So now this is a simple transistor circuit. How about if I want to do more interesting things? I can build more like the passive circuits that we worked with. We had we wanted to, for example, I had a V input here, certain value, and I wanted a V output equal to half of V input. How did I do that? I know that V output, this is R1, R2, V output is equal to V input, R2 over R1 plus R2, right? I know that for this circuit, this is what governs V output, right? So we selected R1 and R2 such that, V output is equal to half of V input. You can select R1 and R2 to make this happen. So we worked with, simple circuits, simple analog circuits, to create, changes in gain. I can make one smaller than the other or bigger than the other, and I can make one frequency dependent. Right? With low pass and high pass filters, we attenuated high frequency and let low frequency pass through, or we attenuated low frequency and we let high frequency pass through. Right? So we did both, gain manipulations as well as, frequency dependent manipulations using simple passive circuits. Right? And then I sort of explained something similar using a transistor circuit. Here, the basic idea is to change for example, I wanted to keep the output current constant by changing this variable resistance. How did I do that? By changing my control signal. So I did that using a simple circuit. How about if I want a more complicated response? I want my output, for example, current to be the integration of my input. What would I do? I would develop a more complicated transistor circuit, because the transistor circuit buys me the fact that I can use an external power supply. The main thing is I can use an external power supply to sort of have my control signal control the output. Right? So the next step is using a more complicated transistor circuit. We will not talk about transistor circuits at all in the course, because an op-amp is basically a more complicated transistor circuit. That's what an op-amp is. So it's a sort of like going from a simple voltage divider to a filter type circuit in analog domain. We went from a simple transistor circuit that is something close to what you understand to a device called an op-amp. That is a complex transistor circuit that does other stuff for us. Okay, that's the background behind the op-amp chapter. So these op-amps are, as we said, they're one example of an integrated circuit. And the name was derived from the fact that with operational amplifier, the first people that started using it were people that were developing the first computers. So computers, what do you want to do with computers? You want to add numbers, subtract numbers, multiply, divide. So what people did was use these op-amp circuits, because these op-amp circuits, again, like the simple versus complicated analog circuits, they allowed us to manipulate the signals in different ways. So people found ways to use these op-amps to make addition, or subtraction, or integration, or division, multiplication. So there are many applications of these op-amp circuits. So we will study a few applications of these op-amp circuits in this chapter. Basically, that's the summary of the chapter, if you wish. So the symbol for the op-amp is this triangle with a plus sign here and this a plus sign. So it has three inputs, two inputs, sorry, and one output typically. And what is not shown here is what? What's not shown here? Remember I said it's a more complicated sort of transistor circuit. So with transistor circuits, the main thing is the external power supply, right? So I would typically also have an external power supply. Sometimes it's positive and zero, and that is called a single rail op-amp, or sometimes it is positive and negative. Right? This would be a positive, this would be a negative. Right? I have a battery that's flipped, and this is called a dual rail power supply, dual rail op-amp, and it's exactly like the transistor circuit. For a dual rail transistor circuit, instead of having just one VG, you have one VG and another negative VG. Then they're both adding, right? They're actually both adding. The nice thing is your your output can be between, if I'm supplying this with a positive value, let's say, and ground, right? If I'm supplying, think of this as a transistor, which means as a variable resistor. If this looks like a variable resistor, then I'm supplying it using a positive value on ground, right? Then the output can perhaps be, if this is a variable resistor, then the output is what? The output, can it be negative? This is my output, V output here. Can the output here across this resistor be negative? Or is it going to be portion of the input voltage? The output is going to be what? This is R, R, R. The output is going to be V input, R over 3R, right, in this circuit. So the output can never be negative, right? But if I change this circuit to a positive value here, resistor here, variable resistor here, a resistor here, and a negative here. And I can make this negative greater than this positive. If I make this negative value greater than this positive value, it's like maybe think of this as 0 and only negative. So the output voltage here will be a portion of the negative input. It's also a portion of the negative. It's V input times the resistance R here multiplied with some of the resistance. So my input voltage is negative in this case, right? So I can have a negative voltage and a positive, negative voltage if I'm supplying with negative. If I have a positive supply and a negative supply, the op-amp is capable of producing a positive output or a negative output, right? So that's another interesting benefit of the op-amp versus a simple transistor circuit. Simple transistor circuit, we looked at simple sort of gain manipulations, etc. But here I can sort of have outputs that are positive, outputs that are negative. I can have outputs that are frequency dependent, and we will see how. So the basic op-amp circuit looks like this, and typically we do not show the power supply. And typically these power supplies are defined by your application, and they're defined by the op-amp construction. Some op-amps cannot accept positive and negative supply. Some can. Okay, so for now, let's just forget about the power supply, as long as we know that this is where the power is going to come from. Think of always, the output power is always going to come from these external power supplies, not from my input signals. Okay? So this is called the non-inverting input of the power supply. That's what's connected to the positive terminal. The negative terminal is it's called the inverting input, and you have an output. We will only study ideal op-amps. We will not study the real op-amps in more detail. We will study and most, for your purposes, for example, or for most purposes, the performance of an op-amp should be ideal. Fine, if you're designing a super high frequency circuit with parasitic, that's a different story, right? But if for the most practical purposes, op-amps, you can think of them as an ideal op-amp. Ideal op-amp behaves, has several definitions. So the ideal op-amp has an output voltage equal to the difference between the non-inverting input and the inverting input multiplied by what is called an open loop gain. A open loop is called the open loop gain. And open loop gain for an ideal op-amp is very close to infinity, very large. So what does that mean? It means that anytime I have a difference between, this is V1 and V2, what will my output look like? V1 is greater than V2. What is the output equal to? If AOL is very high, infinite. It's a large number. It's a very large positive number, right? So practically, of course, this very large positive number will be limited by your external power supply, right? Because this is powered by an external power supply that has, let's say, a maximum value of 15 volts. So anytime you have V1 greater than V2, your output will be driven by the open loop gain of the amplifier to its maximum value. Its maximum value cannot be more than the power supply that is powering it, right? So you can, one application of these op-amps is comparison. If you would like to compare certain phenomena in a physical system, you would put the two phenomena you want to compare here and put an op-amp and look at the op-amp output. And you will know which one of these sensors is producing a higher value. And then you can act upon that in your process, right? So that's one of the simplest application of op-amp circuits. What else? So this is the output voltage. We said that one of the main things about op-amps is, transistor circuits in general, which, an op-amp is nothing but a complicated transistor circuit, is that they do not require input power to be very high. They are actually looking at your input signal and taking the output power from the output power supply, from this power supply that is connected to this op-amp device. So another characteristic is, so besides the open loop gain is infinite, V1 is the voltage at the first terminal. So second slide, I think we'll say that. So it makes sense also that if I'm saying that your input current or your input power is very low, what does that mean? You have these voltage sources that are resembling your sensors, for example. Again, what happened here was, let's say V1 was greater than V2. The output here, did it depend on the current I1? No, it only depended on the difference between the voltages. So really, it's not dependent on the current that's being drawn from your sensors at all. So the ideal op-amp also looks like a open circuit at the input. So it's like a box here with an open circuit at the input. This is called Vx. This is the differential output. Plus minus, this is V1 and V2. If it's really not dependent on the current from your source at all, what it looks like really is an open circuit here, and a gain here, a voltage here, with an open loop gain of A times Vx. So the output here, this is my V out. Okay? So this is what this op-amp looks like. It looks like a box here with three terminals. Of course, a ground terminal, right? So let's say the ground terminal here. There has to be a common point, right? So it looks like, or this is the ground terminal here, right? It's the terminal here, and of course there has to be a common ground to your full circuit. So it looks like two terminals at the input and one terminal defining the output. and the output is defined by the open loop gain, A, times the differential input that you're applying between the two terminals at the input. So this also means that if this is an open circuit, is there current flowing in here? There's no current. So I input in our op-amp circuit will always be I input. This I input will always be 0. It's an open circuit. For all practical purpose, the ideal op-amp looks like an infinite open input impedance. The input impedance here is infinite. Right? And the output voltage depends on the differential input and the open loop gain of the op-amp. Open loop gain is very large, right? So that's op-amp simplistically as a as a representation. But this as itself like that is not super useful. We want to find, so we use it as a comparator, which is great. But we want to see how people use it as filters, how they use it to add, signals at the input, how they use it to subtract signals from the input. We would like to see other applications of the op-amp, and we need to understand the op-amp a little bit more and put some more components around it to be able to do that. Okay? So as it is, the op-amp can only be used as a comparator, just like that. But if we want to make more use of it, we have to add some components around it. So what do you think we want to do? For example, anytime I have a Vx, my output value will saturate. We agree? Because the open loop gain, AOL, is close to infinity. Open loop gain is infinity. So anytime I have a value for Vx, output voltage will be 0. Output voltage will be very large, infinity, saturated with this power supply, right? So this is only good for comparators. So how else can I make use of this? If anytime I have a Vx here, خلاص, I'm done. I cannot use this anymore. It's going to saturate. Either positive or negative or positive and 0. What we can do is sort of take feedback from my output. If my output is very large, right, and I feed some of it back to the input, such that I oppose the voltage V1, for example, or such that I oppose the voltage V1. Remember this Vx here, Vx is equal to V1 minus V2. So if I take some of the output, right, and feed it back, let's say using something like this, like a resistor. So the output voltage is here. This is a very high voltage, right? If this is a high voltage, here there's a resistor, and the voltage difference here, there will be a voltage difference since this is a resistor, and there's a node voltage here, a different node voltage here. So there's a voltage difference between these two nodes, and current will flow. This current will flow, will affect, which will mean that there's a node voltage here that is affected by this current flowing, right? Before I didn't have this resistor. We will see how to include this feedback, but assuming I'm able to include this feedback, is it dependent on the input current? Remember, the feedback is taking a portion of the output. Remember, I'm here taking a portion of the output and connecting it back to my input somehow. Somehow we will discuss how. If I do that, let me look at the output. The output is not dependent on anything but the voltage difference. So now I took part of the output, which is dependent on nothing but the voltage difference, took it back, which means it's like a battery. It's like another battery. So let's say, which means I sort of took a battery and put it in parallel. Of course, I cannot put two batteries that are different in magnitude right in parallel, but let's say I have some impedance between them. There's some impedance. We will put some resistors around them. So if I have a resistor here and a resistor here, and this is some voltage V1, this is some voltage V2, do you agree that the output voltage here, which is the voltage across the parallel combination, is going to be affected by choice of R1 and R2? Do you agree? So, and that's exactly what we will do. We will do that such that the voltage that is being fed back to this node forces Vx to be close to 0, or 0 for all practical purposes, right? If Vx is 0, then my V output is no longer equal to the open loop gain times the differential voltage, because differential voltage is equal to what? Differential voltage Vx, I made it equal to 0, right? I will choose R1 and R2 such that, and I will choose V2. So I will choose R1, R2, and V2 such that I tune the output to be 0, for example, right? If I do that, then my Vx is 0. My V output for the op amp as an open loop circuit or an open loop device is equal to the gain, open loop gain, times Vx. I made this Vx equal to 0, right? Which means that the output voltage is going to be 0 if it's only going to be affected by the open loop gain. But now it's no longer open loop gain only, because I have what? Remember, I connected the resistor here. This resistor is connected to my output terminal, and I'm connecting it to either this one or the other one, right? So now the output voltage is no longer just the open loop gain times the differential voltage. It's also affected by this feedback device. So we will see how this affects in more detail in the next few slides. So you get the concept at least, right? So what we will study is, okay, now we will take this output and bring it back to the positive terminal and see what happens. And this will create a certain family of circuits that have certain applications. And another time we will take this output and bring it back to the negative terminal, and it will create certain types of applications. And another kind, we will take this output and bring it back to the input, but instead of you bringing it back using a resistor, I'll bring it back using a capacitor. What does this do to us? Remember, capacitor current and voltage are related by IC equals CdVc by dt, right? So, which means that I'm bringing back the differential of the input, or the integral of, the integral of the output, or the differential of the output. Let's say I switch the place of, for the feedback, I use a resistor, but at the input here, instead of having these two parallel branches with resistors, I use one with a capacitor, right? So I'm sort of gonna swap, my input signal is now what's being integrated versus my output is being fed back directly, right? That will produce another family of circuits. So this is really what we're gonna study in this chapter. We have time until the computer dies. Okay. So we talked about, there are some more definitions. So VID is the differential signal. I called it VX. So VID, they call this the differential signal, is V1 minus V2. And then there's another definition called common mode signal. Common mode signal is the average of the two inputs. So the op amp has 0 gain for the common mode signal and has infinite gain for the differential signal, right? So if V1 and V2 are the same, what does this mean? It means that the differential input is 0. If the differential input is 0, then the output is going to be 0. The open loop output is going to be 0, which means that the op amp did not amplify my common mode signal, right? Assuming they're equivalent. So these are just some definitions. Let's look at the applications. So op amp amplifiers with negative feedback. Okay? So this would be the general circuit configuration for the amplifiers with negative feedback. Negative feedback means what I was referring to, bringing part of the output and making it negate the effect of Vx. So think of this as follows. Forget about this resistor initially. Right? If you forget about this resistor, what is Vx equal to? What is Vx equal to? Forget about this R2. Forget about R2. What is Vx equal to? Assuming that there is 0 current here. And again, this is not there now. Okay? Forget about this. Come on, guys. This is not there. Remember, this block here looks like this. This op-amp, this block here looks like this thing. This is my V out. So what is Vx? It's Vin, right? Vx is Vin because this is 0 here. This is 0 connected to ground, and this terminal here is connected to my signal from the sensor, for example. And in this case, it's Vin, right? Yes, sir. Remember, this is open loop. This is an open circuit, so there's no current. If there's no current here, then R1, no R1 doesn't really matter. I'm measuring the voltage, right? So there's no current, so there's no voltage drop across this resistor. So there's no voltage drop, then the voltage here is equal to V input. Okay? So now Vx has a certain value equal to V input. What does V output look like? V output is going to be the open loop gain multiplied by Vx, which is the open loop gain multiplied by V input. And open loop gain is infinite, right? So that's not very useful, right? So since it's not very useful, right, so this is the output is AV input, but I forgot to, yeah. Actually the output is not AV input. The output is negative AV input. Can somebody tell me why? Yeah, because V output for op-amp is the open loop gain times V1 minus V2, and this is the non-inverting input minus the inverting input. Remember, the V in here is connected to the inverting input, so the non-inverting, so V1 in this case is 0. So V1 is 0, V2 is V input. So the output is minus open loop gain times V input, which is V2, right? So this is a negative A times V input. So this is like having a big negative battery source, a big negative source. So what would I like to do? I would like to put back this resistor. My objective is to make this Vx go to 0, because I don't want the output to be dependent on the differential input. I want to do something else with the output, right? I want to do something else. I want to only amplify. I don't want to make this output saturate to A times V input. I do not want to do that, because A is an infinite number. It will drive my output to a very large value equal to my power supply. So I cannot see my input signal at all. I want to reduce this A, if you wish. So I've added closed loop. So I've added closed loop feedback to be able to reduce or change the gain of the circuit. At the end, I still want the gain. Like my filter circuits, I still want the gain. The gain is going to be equal to what? The closed loop gain is going to be equal to the output over the input voltage. Now, that is always the case, right? That's what we did with our filters, right? We plotted the magnitude, of the output over the input versus frequency, for example, right? So always I'm interested in this gain of the circuit. If I leave a value of Vx to be large, if there's a certain Vx, then open loop gain will drive my output to infinity, right? to a large value, not useful. I would like to add some feedback so that I can bring Vx to a very, very small value. A very, very small value multiplied by a large number is a reasonably large number, right? That's the objective. So how do you bring this back? I would like to take my output voltage now is a negative number, right? This is, remember, this is the output here is minus A open loop times Vx. This was a negative number. I'm taking part of this negative number and feeding it back to my input. All right? Vx, or the differential input here, Vx, was equal to 0 minus V input. If I find a way to decrease V input, right, then Vx would be, so this was, Vx is equal to minus V input. If I find a way to decrease V input, right, minus something, what did I do? If I find a way to decrease this V input by putting a power supply, remember this is a power supply in this direction, right? This is a power supply in this direction with a resistor. And I bring another power supply with a resistor in its path. So this is like another power supply, V output, with a resistor in its path, right? With a resistor in its path that is going to sort of oppose this original input signal, right? If I do that, what is the effect, right? That's what I did by bringing this back here, right? Connecting a negative, this was a negative number. I took this negative number and put it in opposition with my source here. So I'm opposing what my source was trying to do. If I do that, then I'm going to decrease this Vx. I can, at some point, decrease it to 0 if I want, right? Depending on the value of, if I decrease it to 0, basically if I take a complete short circuit, I'm bringing all the voltage at the output to the input. If I put a resistance, I'm bringing part of the voltage of the output to the input, right? That's what I'm doing here, right? So I can negate it completely by bringing all of the voltage, or I can bring most of it back and negate it for the most part, right? If I make Vx equals 0, then my output no longer depends on the open loop gain, because the open output is equal to open loop gain. My battery is starting to die. No. Yes. So if I bring back part of the negative voltage back here, as I said, the objective is to negate the effect of the input on creating a Vx here. Or shorter, in a simple way, I'm making Vx as close to 0 as possible. Or 0 for all practical purposes. So, and this is called the summing point constraint. This idea of bringing back this feedback such that I make Vx equal to 0. They give it a fancy name, call it the summing point constraint. It also implies what? Yes, sir. There will be current in the feedback resistor, sure, yes. So there will be current, yes, here. There will be current in this resistor. And we will see how to calculate the current in this resistor. So I will show you how to calculate. This current is what? We said that this current is always going to be 0. This I input here is equal to 0. I think it's, as soon as the battery starts dying, the current here is 0, right? Because we said that this thing looks like an open loop, open circuit. This op-amp looks like an open circuit. 2 terminals here, there's an open circuit. If there's an open circuit, that means this current is 0. The current here is always 0. So if the current here is 0, and I have a small amount of current coming in from my sensor, where is it going to go? Exactly, it's going to move in this resistor. So if it moves in this resistor, there will be a voltage drop across this resistor. Right? This voltage drop across this resistor is what's going to define the value of the voltage that's being fed back to oppose the creation of Vx. Right? So now I have what? I have this current equal to 0, the current coming here equal to 0, this current here equal to this current here, and I have Vx equal to 0, because I brought back the voltage to oppose the effect of this source. We'll stop here and we'll continue next time.